Welcome to this comprehensive training on Retrieval-Augmented Generation systems. In today's AI-driven landscape, organizations face a critical challenge. Large language models are incredibly powerful, but they suffer from fundamental limitations that can make them unreliable for enterprise applications. They hallucinate facts, their knowledge becomes outdated the moment training ends, and they cannot access your proprietary data. This training will explain what RAG is, why it has become essential for production AI systems, the complete technical architecture from document ingestion to response generation, and how organizations can leverage secure RAG implementations to transform their operations while protecting sensitive information. Retrieval-Augmented Generation, commonly known as RAG, is an architectural pattern that fundamentally transforms how large language models operate. Instead of relying solely on pre-trained knowledge that becomes stale and may contain errors, RAG systems retrieve relevant information from external knowledge bases in real time and inject this context into the generation process. Think of it as giving an AI assistant the ability to research before answering rather than relying purely on memory. When a user submits a query, the RAG system searches through your documents, retrieves the most pertinent passages, and feeds this verified context to the LLM along with the original question. The result is responses that are grounded in actual, current, verifiable data rather than potentially outdated or fabricated information. The importance of RAG cannot be overstated in our data-driven enterprise environment. Studies show that over 60% of enterprises are already using or testing RAG systems, a dramatic increase from just 31% in 2023. This rapid adoption reflects a growing recognition that standalone LLMs, despite their remarkable capabilities, are insufficient for business-critical applications where accuracy and currency of information are non-negotiable. Organizations in healthcare, legal, finance, and customer service face particular risks from AI hallucinations. A medical chatbot providing incorrect drug interactions, a legal AI citing non-existent case law, or a financial advisor giving outdated regulatory guidance could result in serious harm, legal liability, and reputational damage. RAG provides the architectural foundation to address these risks while unlocking the full potential of generative AI. To understand why RAG has become essential, we must first understand the fundamental problem it solves. Large language models possess remarkable capabilities, but suffer from a critical architectural constraint called the context window. This window represents the maximum number of tokens that a model can process in a single inference call. A token is a discrete unit of text, typically representing approximately 4 characters or 3/4 of an English word. Even as context windows have expanded into the millions of tokens, enterprise reality renders them insufficient. A mid-sized organization might maintain 500,000 documents across contracts, technical specifications, internal communications, research papers, and operational records. A single legal discovery request might involve 2 million documents. Financial institutions routinely manage document repositories exceeding 1 petabyte. Converting these figures to tokens produces numbers that dwarf any context window. A petabyte of text documents translates to roughly 250 trillion tokens, far exceeding what any model can process. Beyond sheer volume, stuffing massive context windows creates practical problems that make this approach unworkable. Inference costs scale directly with token count. Every additional token you push through the model increases your compute bill proportionally. Latency increases dramatically. Users expect responses within seconds, not minutes. Processing millions of tokens introduces unacceptable delays. Most critically, LLM attention mechanisms degrade with context length. Models struggle to maintain focus across extremely long contexts, a phenomenon researchers call lost in the middle, where information in the center of long contexts receives less attention than information at the beginning or end. RAG addresses these constraints elegantly by decoupling knowledge storage from knowledge processing. Rather than forcing all information through the context window, RAG systems maintain external knowledge bases and retrieve only the specific information relevant to each query. The LLM receives a focused, manageable context containing precisely the passages needed to answer the user's question. A production RAG system comprises 2 distinct pipelines that operate asynchronously and serve different purposes. The first is the injection pipeline, also called the indexing pipeline. This pipeline processes source documents into a searchable format. It runs offline during initial system setup and periodically thereafter as new documents enter the corpus. Its output is a populated vector database containing mathematical representations of document content. Think of this as building your searchable knowledge library. The second is the retrieval pipeline, also called the query pipeline. This pipeline handles real-time user interactions. When a user submits a query, the retrieval pipeline searches the vector database, retrieves relevant content, and orchestrates LLM response generation. Latency requirements here are strict because users expect responses within seconds. Understanding both pipelines in technical depth is essential for building systems that actually work in production environments. Let us examine the ingestion pipeline in detail, starting with document ingestion and preprocessing. Raw documents arrive in heterogeneous formats: PDF, DOCX, PPTX, HTML, Markdown, plain text, scanned images requiring OCR, emails with attachments, and spreadsheets containing textual data. The ingestion layer must normalize this diversity into clean, structured text that can be processed uniformly. PDF extraction presents particular challenges that deserve special attention. PDFs are presentation formats, not semantic formats. They specify where characters appear on a page, not what those characters mean. Tables become scrambled text. Multi-column layouts interleave incorrectly. Headers and footers repeat on every page. Figures contain text that extraction tools miss or misplace. Production systems require specialized PDF parsers. Libraries like PyMU-PDF, also known as FITS or PDF Plumber, can handle simpler documents. Commercial solutions like Amazon Textract or Azure Document Intelligence apply machine learning to reconstruct document structure for complex layouts. Metadata preservation matters significantly and is often overlooked in RAG implementations. Document titles, authors, creation dates, section headings, and source URLs provide crucial context during retrieval. A chunk stating, "Revenue increased 15% means nothing without knowing which company, which quarter, and which document it came from. Ingestion pipelines must extract and associate metadata with each chunk. This metadata enables filtering during retrieval, allowing users to search within specific document types, date ranges, or organizational departments. Text cleaning removes noise that degrades embedding quality. Excessive white space, special characters, encoding artifacts, boilerplate headers and footers, page numbers, and irrelevant formatting markers. However, aggressive cleaning risks removing meaningful content such as code snippets, technical notation, and structured data. Cleaning strategies must be tuned to document types. What works for legal contracts may destroy the meaning of software documentation. This is why EPH4's approach of processing documents entirely in the browser gives you control over how your specific documents are handled. We now arrive at chunking, the stage where RAG systems succeed or fail. Chunking means dividing documents into retrievable units. Poor chunking cascades through the entire system. Embeddings capture wrong semantic boundaries, similarity search returns irrelevant results, and LLM responses hallucinate or miss critical information. The fundamental challenge is this: chunks must be small enough to be precise and relevant to specific queries, but large enough to contain sufficient context for the LLM to generate meaningful responses. This tension drives the development of increasingly sophisticated chunking strategies. There is no single chunking strategy that dominates all use cases. Selection depends on document characteristics and system requirements. Let us examine the major approaches and their trade-offs. Fixed-size chunking is the simplest approach and often a reasonable starting point. This method divides text into chunks of predetermined token count, typically 256 to 1024 tokens. Implementation is straightforward. Tokenize the document, split at regular intervals, and optionally add overlap between consecutive chunks to preserve context across boundaries. Overlap prevents information loss when important passages span chunk boundaries. Without overlap, a sentence beginning at token 510 and ending at token 520 would be split across chunks, potentially rendering both fragments semantically incomplete. Industry best practices recommend 10 to 20% overlap as a starting point. The advantages are clear. Predictable chunk sizes simplify embedding model input management and retrieval token budgeting. Implementation requires minimal document understanding. The disadvantages are equally clear. Arbitrary boundaries ignore semantic structure. A chunk might begin mid-sentence, split a paragraph discussing a single concept, or combine the conclusion of one topic with the introduction of another. These semantically incoherent chunks produce embeddings that fail to capture meaningful content. Sentence-based chunking respects grammatical boundaries by splitting only at sentence endpoints. Sentences are grouped together until reaching a target chunk size. This ensures that chunks contain complete grammatical units, and embeddings capture coherent statements rather than fragments. However, sentence boundary detection requires more than splitting on periods. Abbreviations like Dr., Inc., and US create false positives. Decimal numbers like 3.14 and ellipses also trigger incorrect splits. Production implementations use NLP libraries with trained sentence tokenizers, Spacie, NLTK's Punct Tokenizer, or regex patterns tuned to specific document types. The disadvantage is that sentence length varies dramatically. Technical documents might contain 200-word sentences, while social media content might average 8 words. Resulting chunk sizes are inconsistent, complicating downstream processing. Recursive character text. Splitting, popularized by LangChain, attempts to split at the most semantically meaningful boundary available. It tries a hierarchy of separators in order. First paragraph breaks indicated by double new lines, then single new lines, then sentences indicated by periods, then spaces, and finally individual characters. The algorithm recursively applies this hierarchy. First attempt paragraph splits. If resulting chunks exceed the target size, split those chunks at line breaks. If still too large, split at sentences, and so on. The advantage is that this approach preserves the highest level semantic structure possible for each section of text. A document with clear paragraph breaks chunks at paragraphs. Dense text without breaks chunks at sentences. The disadvantage is that results vary unpredictably based on document formatting. Documents with inconsistent formatting produce inconsistent chunk quality. Semantic chunking represents a more sophisticated approach that uses embedding similarity to identify topic boundaries. Rather than relying on textual markers, this method embeds individual sentences, then measures similarity between consecutive sentences. Sharp drops in similarity indicate topic transitions, which become natural chunk boundaries. For example, a sentence about Q3 revenue followed by a sentence about year-over-year growth would show high similarity, around 0.89 indicating the same topic. But if the next sentence discusses a new CEO announcement, similarity drops to perhaps 0.34, signaling a topic shift and chunk boundary. The advantage is that chunks align with actual semantic boundaries regardless of formatting. Each chunk discusses a coherent topic. The disadvantages are computational cost, which scales with sentence count, and the need for threshold tuning through experimentation. Short documents may lack sufficient topic variation to benefit from this approach. Document structure aware. Chunking leverages the explicit hierarchies present in technical documents, research papers, legal contracts, and software documentation. These documents contain chapters, sections, subsections, and headings. Structure-aware chunking parses this hierarchy and chunks within structural boundaries. For Markdown documents, this means splitting at header levels. For HTML, parsing the DOM tree. For PDFs with detected structure, using section boundaries identified by document understanding models. The advantage is that chunks correspond to author-intended organizational units. Retrieval can leverage structure, for example, finding information specifically from the methodology section. The disadvantage is that this approach requires reliable structure detection, which fails on poorly formatted or unstructured documents. Section sizes also vary enormously. A 50-page chapter and a 2-paragraph subsection are both technically sections. Agentic chunking represents an emerging approach that uses LLMs themselves to perform chunking. The document is passed to a language model with instructions to identify semantically coherent passages and propose chunk boundaries. The model analyzes content meaning, identifies topic transitions, and returns boundary positions. This approach leverages the LLM's deep language understanding to make intelligent chunking decisions. The advantage is highest quality semantic boundaries that adapt to any document type without format-specific rules. It can handle complex documents where other methods fail. The disadvantages are significant. This approach is extremely expensive because it requires LLM inference for every document during indexing. Latency makes it impractical for large corpora. Results are also non-deterministic. For high-value, low-volume content, agentic chunking may be worth the cost. For large-scale commodity content, simpler approaches are more practical. EPH4's AI RAG Chunkenizer tool provides an excellent solution for experimenting with chunking strategies. It processes PDF, Word, and Excel documents entirely in your browser with no data leaving your device. This allows you to test different chunking approaches on your actual documents before committing to a production configuration. The tool is open source under MIT license, GDPR compliant, and SOC2 ready. You can view the source code and try the live demo at eph4.ai. When selecting a chunking strategy, consider these guidelines. For well-structured technical documents, use structure-aware chunking. For conversational or informal text, use sentence-based approaches. For mixed-format enterprise documents, recursive splitting works well. For high-value, low-volume content, consider semantic or agentic methods. For large-scale commodity content, fixed size with overlap provides the best balance of quality and efficiency. Many production systems combine strategies, using structure-aware chunking for documents with clear hierarchies and falling back to recursive splitting for unstructured content. Once documents are chunked, each chunk must be converted into a vector representation through embedding generation. An embedding is a list of floating point numbers that captures semantic meaning. These vectors enable similarity search. Chunks with similar meanings produce vectors that are geometrically close in the embedding space. An embedding model is a neural network trained to map text to vectors, such that semantically similar texts produce similar vectors. The training process uses contrastive learning, where the model sees pairs of related texts and unrelated texts, learning to push positive pairs together and negative pairs apart in the vector space. The resulting vector space exhibits remarkable properties. Synonyms cluster together. Analogies manifest as geometric relationships. Documents discussing similar topics occupy nearby regions regardless of surface-level vocabulary differences. The phrase, "the cat sat on the mat," and "a feline rested on the rug" produce nearly identical vectors, while "stock prices rose yesterday" produces a completely different vector. Selecting an embedding model significantly impacts retrieval quality. Key selection criteria include several important factors. Dimensionality refers to vector size and affects storage costs and search speed. Smaller dimensions around 384 are faster and cheaper. Larger dimensions around 1536 capture more nuance. Most production systems use 768 to 1024 dimensions as a balanced choice. Context length defines the maximum input length for the embedding model, typically 512 to 8192 tokens. Chunks exceeding this limit are truncated, losing information. Chunk sizes must align with model limits. Domain specificity matters for specialized applications. General-purpose models like OpenAI's Text Embedding 3 or Cohere's Embed v3 work well across domains. Specialized models trained on medical, legal, or scientific text outperform general models in those domains. Multilingual support is essential for international deployments. Some models embed different languages into the same vector space, enabling cross-lingual retrieval, where a query in English can find relevant documents in Spanish or German. Popular embedding models for production RAG systems include several strong options. OpenAI Text Embedding 3 Large offers 3,072 dimensions with 8,191 maximum tokens. It provides high quality with an easy API. Cohere Embed v3 offers 1,024 dimensions with 512 maximum tokens and strong multilingual capabilities. Voyage AI Voyage Large 2 offers 1,024 dimensions with an impressive 16,000 maximum tokens for long context needs. BGE Large NV1.5 offers 1,024 dimensions with 512 maximum tokens. It is open source and self-hostable. E5 Large V2 offers 1,024 dimensions with 512 maximum tokens and strong zero-shot performance. Production embedding pipelines must handle scale efficiently through batching, which processes multiple texts per inference call to amortize overhead, and parallelization across multiple workers for large corpora. Caching avoids re-embedding unchanged content by hashing chunk content and checking cache before embedding. Embeddings require specialized storage in vector databases optimized for similarity search. Traditional databases excel at exact match queries like finding records where user ID equals a specific value. Vector databases solve a different problem, finding vectors most similar to a query vector according to some distance metric. Common similarity metrics include cosine similarity, which measures the angle between vectors while ignoring magnitude. Values range from -1 for opposite vectors to +1 for identical vectors. This is the most common metric for text embeddings. Euclidean distance, also called L2 distance, measures straight line distance between vector endpoints. Smaller values indicate higher similarity. Dot product is the simple inner product, equivalent to cosine similarity for normalized vectors and fastest to compute. Exact nearest neighbor search requires comparing the query vector to every vector in the database, which has O of n complexity that becomes prohibitive at scale. Approximate nearest neighbor, or ANN, algorithms trade perfect accuracy for dramatic speed improvements. HNSW, which stands for Hierarchical Navigable Small World, builds a multi-layer graph where each node connects to nearby neighbors. Search navigates from coarse upper layers to precise lower layers. This offers excellent query performance with high recall. IVF, which stands for Inverted File Index, clusters vectors into partitions using k-means. Search first identifies relevant clusters, then searches only within those clusters. This is good for very large data sets with acceptable recall trade-offs. PQ, which stands for Product Quantization, compresses vectors by dividing them into subvectors and quantizing each independently. This dramatically reduces memory usage at some accuracy cost and is often combined with IVF. Most production systems use HNSW for datasets under 100 million vectors, switching to IVF-PQ hybrids for larger scale. Several vector database options serve different needs in production environments. Pinecone is a fully managed serverless vector database with excellent developer experience, automatic scaling, and built-in metadata filtering. It has higher cost at scale but minimal operational overhead. Weaviate is open source and supports hybrid search combining vectors with BM25 keyword search. It offers a GraphQL API and can be self-hosted or used as managed cloud. Qdrant is open source and Rust-based for performance. It has strong filtering capabilities, payload indexing, and quantization support. pgvector is a PostgreSQL extension adding vector similarity search. It is ideal when you need vectors alongside relational data without managing separate infrastructure. Chroma is lightweight and embedded, excellent for prototyping and small-scale applications. It runs in process without a separate server. For enterprise deployments where data privacy is paramount, EPH4's approach of keeping all processing client-side eliminates the need to trust your sensitive documents to external vector database providers. With the injection pipeline complete, documents exist as searchable vectors. The retrieval pipeline handles real-time queries, transforming user questions into relevant context for LLM generation. Query processing is the first stage. User queries arrive in natural language, often ambiguous, incomplete, or poorly phrased. Query processing transforms raw input into effective search queries. The simplest approach embeds the user query using the same embedding model used for chunks, then searches for similar vectors. This works well for queries that closely match document language. It fails when queries use different terminology than documents. A user asking how to fix a broken build will not match documentation about resolving compilation errors. Query expansion enriches the original query with related terms, synonyms, or reformulations to improve recall. LLM-based expansion uses a language model to generate alternative phrasings like resolving build failures, troubleshooting compilation errors, and debugging failed builds from the original query. HyDE, which stands for Hypothetical Document Embeddings, represents a clever retrieval enhancement technique. Instead of embedding the question directly, HyDE generates a hypothetical answer to the query, then searches using that answer's embedding. The hypothesis matches document language better than the question. For example, if a user asks, "What is our refund policy?" the system first generates a hypothetical passage like, "Our refund policy allows customers to return products within 30 days of purchase for a full refund. Items must be in original condition with receipt." This hypothetical answer is then embedded and used for similarity search, often finding more relevant results than the original question would. Query decomposition handles complex queries that contain multiple sub-questions. The system breaks them into simpler queries that can be answered independently. For example, compare the Q3 and Q4 revenue and explain what caused the difference becomes 3 separate queries. What was the Q3 revenue? What was the Q4 revenue? And what factors affected revenue between Q3 and Q4? Each subquery retrieves independently, and results are aggregated for the final response. Beyond basic vector search, sophisticated retrieval strategies improve result quality significantly. Hybrid search addresses a critical limitation of pure vector search. It can miss exact keyword matches that users expect. Hybrid search combines vector similarity with traditional keyword search using BM25. The approach retrieves candidates from both vector and keyword indexes, then combines scores using techniques like reciprocal rank fusion. A well-tuned hybrid system might weight vector search at 70% and keyword search at 30%. capturing both semantic similarity and exact term matches. Many vector databases support hybrid search natively. Weaviate, for example, allows you to set an alpha parameter balancing between vector and keyword components. Multi-vector retrieval creates multiple embeddings per chunk, capturing different semantic aspects. Colbert-style late interaction embeds each token separately and computes fine-grained similarity. Another approach embeds both chunk content and an LLM-generated summary, where summaries capture high-level meaning and content captures details. Parent-child retrieval addresses a common problem. Retrieval often returns chunks too small for meaningful context. This technique searches on small chunks for precision but returns larger parent chunks for context. During indexing, you create large parent chunks of perhaps 2,000 tokens, then subdivide each into smaller child chunks of perhaps 400 tokens. Only the child chunks are indexed for search. When a query matches a child chunk, the system retrieves the corresponding parent chunk, providing the LLM with sufficient context to generate a comprehensive response. This approach gives you the best of both worlds: precise retrieval targeting specific passages combined with rich context for generation. Reranking represents a critical stage that dramatically improves retrieval quality. Initial retrieval optimizes for recall, finding all potentially relevant chunks quickly. Reranking optimizes for precision, ordering results by actual relevance to the query. Cross-encoder reranking processes query document pairs jointly, enabling fine-grained relevance assessment impossible with independent embeddings. While biencoders embed query and documents separately, then compare vectors, cross-encoders consider the full interaction between query and document text. Cross-encoders are slower than biencoders, but significantly more accurate. The standard approach is to use them to re-rank a short list of 20 to 100 candidates retrieved by faster vector search methods. LLM-based re-ranking uses language models to assess relevance with nuanced understanding. The system presents the query and candidate results to an LLM, asking it to rank results by relevance and return the ordering. Cohere Re-Rank API provides production-ready re-ranking as a service, offering an easy way to add this capability without building custom infrastructure. Context assembly is the stage where retrieved chunks are combined into coherent context for the LLM. Deduplication removes overlapping or duplicate content. Retrieval often returns similar passages, especially with chunk overlap or multi-query strategies. The system compares embeddings of selected results and filters out chunks that exceed a similarity threshold, typically around 0.9. Token budget management ensures retrieved content fits within LLM context window limits while maximizing information. The system tracks token counts as it adds chunks, truncating the final chunk if necessary to stay within budget. A portion of the budget must be reserved for the query itself and the generated response. Context ordering affects LLM attention. Research on the lost-in-the-middle phenomenon shows that LLMs attend more to content at the beginning and end of context. Strategic ordering places the most relevant content at these positions, with less critical content in the middle. Response generation is the final stage where the LLM produces the answer using assembled context. A basic RAG prompt instructs the model to answer the question based on provided context and to indicate when context does not contain relevant information. This grounding instruction is crucial for reducing hallucinations. Citation and attribution are often required in production systems. The approach numbers each source and instructs the LLM to cite sources using bracketed notation. The response then includes both the answer and metadata about which documents supported which claims. Handling insufficient context requires checking whether retrieved content actually answers the query. One approach uses the LLM to rate context relevance on a 0 to 1 scale. If relevance falls below a confidence threshold, the system acknowledges the limitation rather than hallucinating an answer. This honesty builds user trust and avoids the serious problems caused by confident but incorrect responses. Advanced RAG techniques extend beyond basic retrieve and generate patterns to handle complex use cases. Agentic RAG uses LLMs to orchestrate multi-step reasoning rather than a single retrieval generation cycle. The system decides at each step whether to search for more information, provide a final answer, or ask for clarification. This iterative approach handles complex questions that require gathering information from multiple sources or reasoning across multiple steps. Graph RAG captures relationships between entities and concepts rather than treating documents as independent units. The system extracts entities and relationships from chunks, builds a knowledge graph, and uses graph traversal during retrieval. When a query mentions an entity, The system retrieves not just directly matching chunks, but also chunks associated with related entities. Self-RAG adds reflection, where the LLM critiques its own retrieval and generation, iterating to improve quality. After initial retrieval, the system evaluates whether passages are sufficient to answer the question. If insufficient, it identifies gaps and formulates new search queries. After generation, it verifies that the answer is accurate and complete, regenerating with critique if improvement is needed. Corrective RAG or CRAG evaluates retrieval quality and takes corrective action when results are poor. Each retrieved result is evaluated as correct, ambiguous, or incorrect. If all results are incorrect, the system falls back to web search. If results are ambiguous, it refines the query and supplements with additional sources. Contextual retrieval, developed by Anthropic, prepends chunk-specific context generated by an LLM. Before embedding, each chunk receives context like, "This section describes the Q3 2024 financial results, specifically addressing revenue growth in the enterprise segment." This additional context dramatically improves retrieval accuracy for chunks that would otherwise lack identifying information. Evaluation and optimization require systematic measurement and continuous improvement of RAG system quality. Retrieval metrics include recall at K, which measures what proportion of relevant documents appear in the top K results. Mean reciprocal rank, or MRR, measures how high the first relevant result ranks. Normalized discounted cumulative gain, or NDCG, accounts for graded relevance rather than just binary relevant or irrelevant classifications. End-to-end metrics include answer correctness, comparing generated answers against ground truth for factual accuracy, completeness, and relevance. Faithfulness measures whether the answer only contains information from retrieved context, detecting hallucinations. Answer relevance evaluates whether the answer actually addresses the question asked. Building evaluation datasets requires curating test sets with question-answer pairs generated from your actual documents. Ground truth answers and source evidence enable systematic measurement of system performance. Optimization strategies include several important approaches for improving RAG performance. Chunk size tuning tests different chunk sizes against your evaluation set. The optimal size depends on your documents and queries. Some systems benefit from smaller, more precise chunks, while others need larger chunks with more context. Embedding model comparison evaluates different models on your specific domain. General-purpose models may underperform compared to domain-specific alternatives for specialized content. Hyperparameter. Search explores combinations of chunk size, overlap, top K retrieval count, re-ranking settings, and hybrid search balance. Grid search or more sophisticated optimization techniques can identify the best configuration for your use case. Continuous monitoring tracks metrics over time. Recall shows whether you are retrieving relevant chunks. Precision shows whether those chunks are actually useful. MRR and NDCG measure ranking quality. Performance may drift as your document corpus evolves, requiring periodic reevaluation. Production considerations introduce engineering challenges beyond core retrieval logic. Scalability requires horizontal scaling through vector database clustering, sharding strategies that partition data across multiple indexes, and careful capacity planning as your corpus grows. Latency optimization involves caching frequent queries and their results, async processing to parallelize independent operations, and careful tuning of retrieval parameters to balance quality and speed. Monitoring and observability require tracking key metrics, including query count, latency distributions, retrieval scores, and user feedback. Structured logging enables debugging when issues arise, alerting surfaces problems before they impact users. Security considerations are critical for production RAG systems handling sensitive data. Access control must implement document-level permissions. Users should only retrieve documents they are authorized to access. This requires filtering retrieval results based on user identity and document permissions. Prompt injection. Defense sanitizes retrieved content before including it in prompts. Malicious content in documents could attempt to override system instructions or extract sensitive information. Patterns like ignore previous instructions should be filtered or flagged. Data privacy is paramount when RAG systems process sensitive documents. EPH4's ephemeral RAG pipeline addresses this by processing documents entirely client-side with AES 256 encryption at rest. No data leaves your device. Sessions are isolated and leave no trace after interaction. You maintain complete control over your data outputs and verifications. Document freshness requires keeping indexes synchronized with source documents. Incremental indexing detects documents modified since the last sync. Deleted documents must be removed from the index. Modified documents require re-chunking and re-embedding. New documents must be processed and added. Version control enables rollback if index updates introduce problems. Audit trails track what was indexed when, supporting compliance requirements. For organizations handling sensitive or regulated data, EPH4's approach eliminates synchronization concerns by processing documents on demand rather than maintaining persistent indexes of confidential information. Common pitfalls in RAG implementations include several frequently encountered issues. Chunks lacking context occurs when a chunk states, "The increase was 15% without indicating what increased. Solutions include contextual chunking that adds document and section information, or Anthropic's contextual retrieval approach. Semantic search missing keywords happens when searching for HIPAA compliance, fails to find documents mentioning Health Insurance Portability and Accountability Act. Hybrid search combining vector and keyword approaches addresses this, as does acronym expansion during indexing. Retrieved context. Contradicting itself occurs when different documents contain conflicting information. Timestamp awareness helps prefer newer information. Conflict detection can alert the system to present information with appropriate caveats. Long documents losing information results from the lost-in-the-middle attention degradation. Hierarchical indexing with summaries at multiple levels helps surface important information regardless of its position in original documents. The system hallucinating confidently. Despite having context is a serious issue requiring multiple mitigations. Clear prompting instructs the model to answer only from provided context and to acknowledge when information is insufficient. Faithfulness checking verifies each claim in the answer against the context, flagging unsupported assertions. Uncertainty. Quantification estimates confidence based on context relevance, allowing the system to express appropriate hedging when confidence is low. Human oversight remains important for high-stakes applications. RAG systems should surface sources and confidence levels, enabling humans to verify critical information. In conclusion, Retrieval-Augmented Generation transforms large language models from isolated reasoning engines into knowledge-connected systems capable of grounding their responses in specific, verifiable information. The architecture presented in this training spans document ingestion, intelligent chunking, vector storage, sophisticated retrieval, and faithful generation. Each component requires careful design and continuous evaluation. Success requires attention to every stage of both pipelines. Poor chunking produces poor embeddings. Weak retrieval surfaces irrelevant context. Insufficient prompt engineering leads to hallucinated responses. Yet, when each component is carefully designed, RAG systems achieve remarkable capability, answering questions from vast document collections with accuracy and specificity that neither pure LLMs nor traditional search can match. The field continues advancing rapidly. Techniques like contextual retrieval, graph RAG, and agentic orchestration push the boundaries of what these systems can accomplish. As embedding models improve, vector databases scale, and LLMs become more capable, RAG architectures will remain central to practical AI applications. For organizations handling sensitive documents, EPH4's encrypted ephemeral RAG pipeline provides a path to leverage these capabilities while maintaining complete data privacy. All processing occurs in your browser. Data is AES 256 encrypted at rest. Sessions leave no trace. You maintain control. Building effective RAG is an engineering discipline requiring systematic experimentation, rigorous evaluation, and continuous optimization. The techniques and patterns in this training provide the tools. Applying them to your specific domain and use case is where the real work begins. Start a free session at eph4.ai without registering. We only use access keys for data security. Experience secure AI document analysis that leaves no trace.